This lesson is about chemical reactions and how we represent chemical reactions with word equations in a specific format and in the form of balanced symbol equations. And we'll also be looking at law of conservation of mass, which is to deal with all chemical reactions. And to understand this, we need to know and be familiar with these words: reactants, products, and what it means by balancing a chemical equation. To be able to write word equations, one should understand a description of a chemical reaction. For instance, I have given an example here at the top where the words are highlighted for a particular reason. I'll come into that in a moment. Now, if you read that full description of a chemical reaction, it reads as: magnesium reacts with sulfuric acid, forming magnesium sulfate and hydrogen gas. Now, to write a word equation, one should be able to recognize which are the chemical substances that are mentioned in the description, which is here magnesium, sulfuric acid, magnesium sulfate, and hydrogen. Now, there are also descriptive words such as these. This reacts with, which shows that these two are reacting together, and they're called reactants. So, and then these two words are the products, because it says forming, which means it is making these new substances, magnesium sulfate and hydrogen gas. So the two substances that are reacting together, they are called reactants, and the new substances that are produced are called products. Now, it is not always two substances. Sometimes it's one substance only. Sometimes it can be two, three, or even four. It doesn't matter how many substances there are. We need to be able to recognize these substances. But at GCSE level, we would have a maximum of 2 to 3 substances. And this has been converted in a particular format when you write a word equation. Like so, you pick the two reactants, here magnesium and sulfuric acid, and you need to use a plus in between here, the plus symbol, showing that these two are the reactants and they are reacting together, and an arrow to separate the reactants from products. So the products are here again separated by that plus in the middle, just to show that this is one substance plus another substance is made, and if it is a third substance made, you need to show that with another plus here and write the name of that substance. So the key skills involved here are being able to recognize the names of chemical substances and be able to recognize which are the substances that are reacting together, which are the products that are made, the new substances that are made in a chemical reaction. You do not have to write this reactants and show which substances are the reactants and the products unless it's specifically asked in the question. So if it is asked in the question to name the reactants, then you just name these two, and if you're asked to name the products, then you write just these two names, and you may want to annotate like that. But otherwise, if you're asked to write word equation, this itself is sufficient. You may want to try to write a word equation for the description given here. Now you may want to pause the video for the time it takes for you to try to write a word equation for the description of a chemical reaction that's given here. I guess you must have tried writing a word equation for at least A now. However, if you're finding it difficult, I'm going to start off by identifying the names of the chemical substances that are involved here. Magnesium is one substance, and hydrochloric acid, the second substance, hydrogen, third substance, and magnesium chloride is the fourth substance. Next is to realize and recognize which two are reacting together, and it's pretty clear here. Magnesium reacts with hydrochloric acid, so these two are the reactants to form, which means that they are produced. These are the new substances that are produced: hydrogen gas and magnesium chloride. I guess you must have tried question number A now. Time to check this. Magnesium and hydrochloric acid are the reactants, so I have written like this, separated by a plus. It doesn't matter which order you got this. You might have got hydrochloric acid here and magnesium over there. That's okay. Arrow, hydrogen is one of the product, and then magnesium chloride, the second product. I hope you got this right. Now you may want to try to write word equations for the rest of the questions, and once you've done this, check back again for the answer. Pause the video at this stage now and try out your word equation, the rest of the exercise. I'm going to now underline all the chemical substances that are mentioned in each of these chemical reactions to start with, and then put the answers up so you can check your work. As you can see here, all the chemical substances that are involved and mentioned in each of the chemical reactions have been underlined now. So all you had to do is to further identify the reactants, which substances are reacting together and which substances are the products. Sometimes it can be just one substance which is a reactant, or there may be just one product. It doesn't matter how many, but we should be able to recognize that. Once you're done your word equations, check your answers on the next slide. It's time to check your answers. Make sure you got all of these correct. Please note that water is also a chemical name, as well as it's a common name. We use that to refer to water in everyday life, but it is also a chemical name. But when we refer to salt, it is actually sodium chloride. Sodium chloride is a chemical name, but salt is a common name. But water is both. It is also allowed to write the reaction conditions. For example, here on reaction G, under the arrow, you can write the reaction condition, which in this case is heat. As you have to heat sodium hydrogen carbonate for this reaction to happen, we are allowed to write heat, but it's under the arrow, not here. For example, you can't write plus heat here because heat is not a substance and it is not one of the reactant or the product. It is just a condition. Here is another example of what you can write on above or below the arrow. What's given here is again reaction conditions. Aluminum oxide is a catalyst in this reaction where octane is cracked to produce hexane and ethene. This reaction is called cracking reaction. You will learn it in when you learn about oils, crude oil and its uses. Aluminum oxide does not take part in this reaction. It is not a reactant or a product. It is just a catalyst, which means it speeds up the reaction. So it is one of the reaction conditions apart from heat. So you can write heat above or below the arrow as with aluminum oxide. Click on the next slide to progress and learn about balanced symbol equations. Here is a chemical reaction where hydrogen gas reacts with oxygen gas to produce water. As you can see here, hydrogen molecule is made up of 2 atoms of hydrogen, and oxygen molecule is made up of 2 oxygen atoms. And you see the double bond here. It's got 2 chemical bonds connecting the oxygen atoms. What you also see here is water molecule, and it's connected to 2 hydrogen atoms here. And this is just a basic equation, and it's not balanced. In symbol form, we write it like this. As you already know, this 2 represents this 2 is for the 2 hydrogen atoms, that 2 is for the 2 oxygen atoms, and this H2O stands for the water molecule. And the 2 hydrogen atoms that you see here represent that there are 2 hydrogen atoms in one molecule of water, and there is 1 oxygen atom here showing that 1 oxygen atom in the molecule. Now we're going to try and balance this equation. This equation is not balanced. One of the most important things that you should do when you try to write balanced equation is to leave spaces before the molecules or substances involved or elements involved. And whenever you write a chemical equation, leave a space here, because that's where you would put numbers to balance the equations. Another thing to remember is you are not allowed to change these numbers, which are subscripts. That shows how many atoms are present in the molecule. Now you cannot change this and produce a different molecule. You cannot change the formula for the molecule. It stays as it is. So you're not allowed to change these numbers. You're only allowed to put numbers in front to balance the equation to get the same number of atoms on the left hand side as there are on the right hand side. What you see here is one way of doing this. I have listed out the number of atoms, the atoms that are present in the reactant side, hydrogen and oxygen, and the atoms that are present on the reactant on the product side, which is hydrogen and oxygen. Now all we have to do is try and balance this equation, make sure the number of atoms on both sides are the same. I'm going to start off with the hydrogen. You got 2 hydrogen here, so I'm going to write 2 here. There are 2 oxygen atoms here, so I'm going to write 2 here. And similarly, as you can see here, there are on the right hand side you've got 2 hydrogen, but there is only 1 oxygen here. So I'm going to put a 2 here to make that oxygen number into 2. Now when you put a number in front of a molecule, that applies to every single atom that you got there. So this 2 applies to that oxygen, which means you got 2 oxygen atoms now. It also means that this 2 applies to hydrogen, which now turns into 2 times 2, 4 hydrogen atoms on the right hand side. Remember, you only got 2 here, so that changes the number of hydrogen atoms as well. Now number of oxygen atoms are okay on the right hand side, as now you have 2 oxygen atoms. By just putting that 2 here on the right hand side in front of the water molecule, you've got 2 oxygen atoms. However, now you've got 4 hydrogen atoms, so I'm going to change this into 4. Now to make the number of hydrogen atoms on the left hand side the same as this on the right hand side, which is 4 hydrogen atom, I have to now write a 2 in front of that hydrogen atom. Now by just putting that 2 times 2, it becomes 4 hydrogen atoms on the left hand side. So you got 4 hydrogen atoms on the left hand side. So I'm going to cross this out and put 4 here. And we got now 2 oxygen atoms, and that hasn't changed. Here you got 2 oxygen atoms. So now you can see you got the same number of atoms on the left hand side. For example, hydrogen is 4 and hydrogen is 4 on the right hand side. 2 oxygen atom on the reactant side, 2 oxygen atom on the product side. So now the equation is balanced. It makes sense. If you look at the diagram here, what you have here is 2 hydrogen atoms, and that is present here, so that's okay. But if you look at the oxygen atom, there's 2 oxygen atoms, there's only 1, and its particles cannot just disappear or appear from nowhere. So let's try and understand what we have just done by balancing this equation in this way. It's actually 2 molecules of hydrogen reacting with 1 molecule of oxygen to produce 2 molecules of water, and it's not possible for 1 molecule to react with 1 molecule of oxygen to produce 1 molecule of water, and that's what this really means. So when hydrogen reacts with oxygen, this is the ratio that they react in. You have 2 molecules of hydrogen reacting with 1 molecule of oxygen to produce 2 molecules of water. In this way, we have the same number of atoms on the side of the reactants as well as the products. So if you look at the hydrogen, you got 4 hydrogen atoms, 1, 2, 3, 4 on the reactant side as well. You have 2 oxygen atoms here on the reactant side, and you got 2 oxygen on the product side. Now let's look at more exercises on balancing equations on the next page. It is also useful to write the state symbols next to the chemical symbol for each of the substance that is taking place in the reaction. For example, here you can write G to show that hydrogen is a gas and oxygen is a gas. Water is a liquid, as we know, but it is produced as a gas in this reaction because it's exploded But it's okay to write as that as a liquid as well. If you want, you can write that as a liquid, just to show that what state it is in. That's L for liquid. So for gas it's G, and for liquid it's L, and if you do produce a solid, you write S for solid. I'm going to now show the same method of balancing equation by trial and error for each of these equations here, but you may want to pause the video at any time that you want to try first and then check the working out and then the answer to each of these equations. Let's start with the first equation here, which is this one here. I've written that here. 2 hydrogen atoms on the reactant side. It's only one here, so I can start by writing a 2 in front, and that will make 2 hydrogen atoms on the right hand side. But that 2 applies to that chlorine as well. Now you have 2 chlorine atoms on the right hand side, which balances this chlorine. So that equation is balanced because you got same number of atoms on both sides of the equation. You may want to write down the list of atoms present on the reactant side as well as the product side, and do it like we did before earlier, and do the number of atoms on the left hand side and right hand side, and keep changing the number until you get the numbers of atoms on either side balanced. Let's go into the second equation now, and as you can see here, I have left some space in front of each of the substances, so I can put some numbers here on a trial and error basis to try and solve this, trying to balance this equation. So I'm going to start looking at the number of atoms present on either side. You got 2 magnesium here. It's partially balanced already. There is a 2 here, so that means you have to put a 2 in front of this to have the same number of magnesium atom, which is what I'm going to do now. So a 2 here, and then that number 2 applies to that oxygen, so that you got 2 oxygen atoms on the product side, which balances with this. So now that equation is balanced, except I have to add the state symbol. For magnesium oxide being a solid, I put an S there. The third equation is something that we've looked at earlier in the last page, so I'm not going to go through this again. Let's go into the fourth equation here. There's some substance missing here, and it's a very common chemical reaction where calcium carbonate is heated very strongly to produce calcium oxide and carbon dioxide, and that's a thermal decomposition reaction. So I'm going to write that equation here. Calcium carbonate having calcium oxide plus carbon dioxide. I'm not going to this time include all the state symbols because as the point of this is just to show how to balance equations. So I'm going to leave the state symbols for now, but you may want to include that when you write balance symbol equation. It's always a good practice. Now if you're asked to just balance the equation, these state symbols are not taken into account. So you can, that's of not the priority for the moment. Okay, so let's look at this equation here. You got 1 calcium here, so that's balanced. 1 carbon here, 1 carbon, so that number seems to be the same. 3 oxygen on the left hand side, you got 1 plus that 2 oxygen, you got 3 oxygen on the right hand side as well. So this equation is balanced without having to add any numbers in front of the substances, and this sometimes happens. Some equations do not require you to do anything to balance, it's already balanced. Let's have a look at this last equation here. As you can see, there's only one space here, so this looks like you need to add just one number in front of this hydrochloric acid molecule, hydrogen chloride molecule, to balance this equation. Let's have a look. Start with hydrogen atom here. 1 hydrogen on the left hand side. You have 2 here, so it's pretty obvious that you need to put a 2 in front of that molecule, hydrogen chloride molecule. Now you've got 2 hydrogen atoms here, you have 2 hydrogen atoms here, 2 chloride atoms here, 2 chlorine atoms here, 2 chlorine atoms. So that is balanced. 1 calcium, 1 calcium, 1 carbon, 1 carbon, 3 oxygen atoms. That 2 plus 1, that gives you 3 on the right hand side. So oxygen seems to be balanced. By just putting that one number, the entire equation is balanced. On the next page, we will be looking at more complex equations, a little bit more challenging chemical equations to balance. It's really worthwhile trying them too. If you want to try these equations for yourselves, then pause this video right now, try these equations and come back to this later to check the answers. So if you want to try these equations, pause this video now. I'm going to start with this first equation here. As you can see, there are 2 iron atoms here. Fe is the symbol for iron. There's only one atom here. So I can start by writing a 2 here in front of the iron. It may be wrong, but I'm going to just try with that one. Now, if you look at the oxygen atoms on the left hand side, it's 3 plus 1 here, but there's only 2 here. So you got 4 on this side, you got 2 here. So you may want to try a 2 in front of the carbon dioxide on the right hand side to make that oxygen into 4 now. But by doing that, you have now got 2 carbon on the right hand side, only 1 carbon on the left. So then you would be tempted to put a 2 here, and as you can see now, that has changed the number of oxygen atoms, but it appears that we are going in cycles. So the 2 obviously has not worked. Another useful thing to bear in mind is that you may want to try and make these numbers even, not odd numbers. So as you can see, by putting that 2 here, you got 5 oxygen atoms, 3 here and 2 here, 5 oxygen atoms, whereas you got 4 here. But it looks like you have a problem with the carbon atoms. So once you're happy with the carbon atoms, when you balance the carbon atoms on both sides, then you have a problem with the oxygen, and vice versa. So you may want to try out another number here. So I'm going to try putting a 3 here. Earlier we had 2, obviously that didn't work, and I'm going to put a 3 here, hoping that by doing that I have an even number of oxygen atoms. 3 oxygen atom here, 3 oxygen atom, we got 6 here. So maybe that will work. 2 did not work, obviously. So I'm going to put now a 3 on this side as well. Now as you can see, this has solved the carbon number of carbon atoms on this side and this side. So you got equal number of carbon atoms on both sides. And also if you look at the oxygen atom, 3 oxygen plus 3 oxygen, 6 oxygen on the left, 3 times 2, that's 6 oxygen atom on the right hand side. So the oxygen atoms are now balanced. If you look at the iron, there is 2 iron atom here, so I want to put a 2 in front of this iron on the right hand side to make that equal to the number of atom here. So iron is balanced. Carbon, 3 carbon here, 3 carbon here, 3 oxygen plus that 3, 6 oxygen on the left hand side, and you got 3 times 2, 6 oxygen on the left hand side, on the right hand side. So now that equation is balanced. Now let's have a look at the second reaction here, where you can see there are 2 nitrogen atoms here, whereas there's only 1 here. So I may want to start by putting a 2 in front of that. But by doing that, you have changed the number of hydrogen atoms. 2 times 3, you got 6 hydrogen atoms here, whereas you've only got 2 here. So to make this into 6, I'm going to put a 3 here in front of this hydrogen molecule. So now that makes the equation balanced. As you can check once again, 2 nitrogen atom, 2 nitrogen atoms, 3 times 2, 6 hydrogen atoms, 6 hydrogen atoms, 2 times 3. Now the equation is balanced. Let's have a look at this equation now. You can see there are two aluminum atoms here. There's only one aluminum atom, so I'm going to start by putting a 2 here. Now check the oxygen atoms. 2 oxygen atom. Here you got 3. Now because you've only got oxygen in one place here, you're allowed to put 1.5 here in front of this. I'll explain why in a moment. Okay, so 1.5 is 1.5. Okay, 1.5 times 2, that gives you 3 oxygen atoms. So by doing that, this is the last thing that you're balancing. There's only 2 things here. You've balanced aluminum just now by putting that 2 here. You look at oxygen, that's 3 here, and there's only 2 here. So it's going to be a bit tricky putting a 3 here and making this into 6 and so on. So instead of that, because you've only got that oxygen to balance on the left hand side, to make that equal to 3, you may want to put a 1.5, which is 1.5 there. The idea being, when you multiply that with this 2 times 1.5, that gives you 3. So this equation is balanced. However, if you do not like to see a fractional number here, a decimal place number, then what you need to do is multiply everything by 2. I'm going to show that right now. So I'm going to be multiplying this 2 by 2, and that by 2, and that by 2. There is a 1 here, although it's not written here. So the numbers double up, and this 2 now is going to become 4. This was originally 1.5, so that becomes now 3. 1.5 times 2 is 3. There was 1 here before, and now you multiply that by 2, and it becomes 2. It's worthwhile checking this once again. You got 4 aluminum here, 2 multiplied by 2, you got 4 aluminum here. 3 times 2, 6 oxygen here. 2 times 3, you got 6 oxygen here. Let's have a look at this equation now. 2 carbon atoms here, 1 carbon atom. So I'm going to put a 2 here. Now 6 hydrogen atoms on the left hand side, only 2 here. So I'm going to put a 3 right here. So that makes the number of hydrogen atoms 6. 3 times 2, 6. 6 here. Carbon is okay, hydrogen is okay. Now look at the oxygen atom. 2 oxygen atoms here. 2 times 2, that's 4 oxygen plus that 3. That's an odd number. 7 oxygen atoms on the right hand side. Now there's only 2 oxygen here, but it appears only here. We have balanced everything else. As you can remember, we balanced the carbon, we balanced the hydrogen. The only thing that remains is oxygen now. But you have a problem because you got an odd number. 2 and 2 times 2, 4 plus 3, 7 oxygen atoms on the right hand side. So to make this into 7, instead of changing everything else, you may want to put a 3.5 here, like you did before in the previous equation. So by putting the 3.5 here, it now becomes 7 oxygen atom. 3 times 3.5 multiplied by that 2, that gives you 7 oxygen atoms on the left hand side here. 2 multiplied by that 2, that gives you 4 oxygen plus that 3 oxygen, that gives you 7 oxygen on the right hand side. Now check everything once again. 2 carbon atoms, 2 carbon atoms on the right hand side. 6 hydrogen atoms on the left. 3 times 2, 6 hydrogen atoms on the right hand side. 3.5 times 2, 7 oxygen atoms on the left. 4 plus 3, 7 oxygen atoms on the right hand side. That equation is balanced now. But if you don't like the fractional numbers, you know what you have to do is multiply all these numbers by 2. So I'm going to do that right now. Rewriting this equation over here, is now I'm going to multiply everything by 2. That's 2C2H6 plus 7O2 4CO2 plus 6H2O. Again, it's worthwhile checking this once again. 4 carbon atoms, 4 carbon atoms, 12 hydrogen atoms here, 12 hydrogen atoms here, 14 oxygen atoms, 8 plus that 6 gives you 14 oxygen atoms. Now that equation is exactly the same as that, but you don't have the fractional numbers anymore, you got the whole numbers. Now let's have a look at this equation here. You have one calcium, calcium's the same number of atoms on both sides. You got one hydrogen, two hydrogen here. So you may want to start by putting a 2 in front of this nitric HNO3 molecule. So that makes 2 hydrogen atoms on the left, 2 hydrogen atoms on the left, 2 nitrogen atoms on the left. You have 2 nitrogens on the right hand side as well. Remember, if you have a bracket, you have to multiply that number into everything. And nitrogen is there's 1 nitrogen here. That 1, multiply that by 2, so you got 2 nitrogen atoms on the right hand side. So nitrogen's okay. 2 multiply by the 3, you have 6 oxygen atoms on the left hand side. You have 3, multiply that by that 2, that gives you 6 oxygen atoms on the right hand side as well. So oxygen is also balanced. You have balanced all the atoms in this equation now. Check once again. Calcium 1 1, 2 hydrogen, 2 hydrogen, 2 nitrogen, 2 nitrogens, because that is it's multiplied into the bracket. 2 times 3, 6 oxygen atoms here. 3 times 2, 6 oxygen atoms on the right hand side. So that equation is balanced now. Let's have a look at the law of conservation of mass and apply that to chemical reactions such as here. The law states that the total mass of all the reactants in a chemical reaction is equal to the total mass of all the products. So the mass of hydrogen and oxygen should be equal to the mass of water produced in this chemical reaction. Now this allows you to predict the unknown mass, the mass of substances. It can be products or reactants. This allows you to work that out from knowing the masses of the reactants, or if you know the mass of one of the reactant and the product, it allows you to work out the mass of the other reactant. Now let's apply the law of conservation of mass to this equation. The law makes sense because you've already balanced the equation, and as you know, the total number of atoms that's present in the reactant side should be equal to the total number of atoms present on the product side, and that means the masses should be the same, because the number of particles that you have, the number of atoms of each element or compound that's present on either side should be the same in a balanced symbol equation. And that's what the law of conservation of mass is about. So let's apply that to this chemical reaction here. Some masses are given. 2 gram of hydrogen is reacting with 16 gram of oxygen to produce some water we don't know the mass of. And if you just apply the law of conservation of mass to this reaction, all you have to do is apply that, and this 2 gram, 16 gram, if you add them together, you should get the mass of the water. So in this case, it will be 18 grams. I've just simply added these two together to get this. Let's extend this a little bit more now. What if this is 4 grams and you don't know this, and if this is 36 grams? What will be the mass of the oxygen that will be needed to react with hydrogen to produce 36 gram of water? Again, you apply the law of conservation of mass. So if you add these two, you should get 36 grams. So this means 4 plus a number equals 36. So as you can see, this is obviously 32. So the missing mass is 32 grams. You can also work this out in a different way. All the masses of all the substances have been doubled. 2 grams has become 4, 18 grams becomes 36, and so 16 should become 32. This is true for any chemical reaction. They react in the same ratio. For instance, here it's 2, 16 and 18. So if you double that, and it goes in the same ratio. And what if I extend this a little bit further and make this into 1 gram? So 1 gram of hydrogen is reacting with 8 grams of oxygen. What will be the mass of water that will be produced? Again, as you can see, now I have halved the initial masses. So 2 has become now 1, 16 has become 8. So that 18 should be halved as well, because as we know they react in the same ratio. So 18 half becomes 9 grams. So this allows you to predict the reacting masses once you know the ratios. So let's do another example of reacting masses. Let's have a look at this reaction here. Nitrogen reacting with hydrogen producing ammonia. We know the mass of nitrogen is 28 grams and the mass of ammonia produced is 34 grams. So the unknown quantity here you should be able to work this out by applying the law of conservation of mass. Pause the video now to work it out for yourself and then check the answer in a few minutes once you're done. I hope you have worked this out as 6 grams of hydrogen. As you can see from here, if you add 28 plus 6, that gives you 34. In other words, if you don't know this, you know if you add these two, you should get this number. So you may want to write down this as an equation if you prefer that way. So 28 plus x equals 34, and x would be equal to 34. Take away 28. That gives you 6 grams. So what now if this is 14 grams and this is 3 grams? How much ammonia would be produced? As you can apply the law of conservation of mass again, it's going to be in the same ratio. The sum of these two should be equal to that. And as you can see, this is going to be 17. You should also notice that it is still in the same ratio. This has become half now to 14. This divided by 2 gives you 3, and that divided by 2 gives you 17. You can have a go at this. Try to solve this equation to find the mass of magnesium in this case, and here the mass of magnesium as well as the magnesium oxide. Pause the video now, check your answers later. Okay, now for the answers. You should have got 24 grams here. Now that is because you have 40 grams is the mass of the product, magnesium oxide. You have 16 and some unknown mass of magnesium. Now if you add these two together, you should get that. So what number would go here to give you 40? And it's going to be 24. Or you can make an equation for the 16 plus x equals 40, and to find x you need to take away 40, take away 16 will give you 24. On the second line here you have two unknown quantities. However, if you look, as you already know, they all react in the same ratio, and look for a connection between 16 and 4. As you can see, that has been divided by 4. 16 divided by 4 gives you 4. So that means every other reacting quantity should be divided by 4. So dividing 24 by 4 should give you 6 here. And in the same way, if you divide 40 by 4, that gives you 10 here. So you have established now that this is the reacting quantities, the missing ones, by just knowing one and by solving the first line. you're able to solve the second one by applying the ratio rule. By 16 divided by 4 has given you this, so you should apply the same ratio here. You divide by the same number, you get the missing answers. If you want to know a little bit more about how to write the reacting ratio, the reacting masses of every substance in a chemical reaction, from knowing their atomic masses, relative atomic masses, or relative molecular masses, go to the next page. However, that is not part of GCSE science. You will be learning that in GCSE additional science. But it does help to make sense of the ratios you see here. To understand reacting masses a little bit more, what you will need is to have access to a periodic table. And let's consider the same reaction that we looked in the previous page. Now, if you look at this equation, it's a balanced symbol equation. And now what you need to look in the periodic table is, for the symbol of magnesium, you will find two numbers. There will be a bigger number and a smaller number. The bigger number gives you the mass number of magnesium. You need that number and you write it underneath that equation. And you will need to know the mass of oxygen in the similar way, which is 16. Now 16 multiplied by 2, the molecular mass of this oxygen here is 32. So I will write 32 here. And if you look at magnesium oxide, you just have to multiply these two numbers, 24 plus 16, to get the molecular. And now for the mass of magnesium oxide, the formula mass of magnesium oxide is 24. Add that with the 16. That gives you 40. So I'm going to write 40 here. Now all I have to do is multiply by the numbers in front of magnesium, like so, and 2 times magnesium oxide. What I have got here is the actual reacting masses, and by looking at the periodic table, you are able to write the reacting masses with no other information from just the balanced symbol equation. So now this becomes 48 here. That remains 32. I can put a gram here because what this gives you is the mass in grams, and 80 grams. You can check again. If you add these two numbers, you do get 80. So what this means is, if you have 48 grams of magnesium, you will need 32 grams of oxygen to completely react with it, and you're also be able to predict that you will get 80 grams by reacting these two substances, magnesium and oxygen. And if you have 48 grams of magnesium and oxygen 32 grams, you will get 80 grams of magnesium oxide. This is what makes balanced symbol equations very, very useful. For example, you can even stretch this further. If I divide this number by 10 and this by 10 and this by 10, I get a different ratio of reacting substances. I'm going to write that here, 4.8 grams. So if I take 4.8 grams of magnesium, I will need 3.2 grams of oxygen to react with it completely, and I will get 8 grams of magnesium oxide. You can predict for any given mass of substances using this ratio.